Welcome back to Calculus 3. I'm Dr. Jeff Groh. We're going to begin our discussion today by talking about polar coordinates. To have a coordinate system, you need what is called two foliations of the plane. You can think of these stacked curves as like leaves in a book. You need two intersecting foliations. You can select one point of intersection to be the origin, and then you can move, say, 1 unit over, 3 units up, and describe all of the points in the plane. In space, the foliations take the form of little sheets, like pages in a book, almost, but of course, to fill out all of space, these would have to go either unbounded, at least some of them. They could form little nested spheres. Einstein used to talk about curvilinear coordinates, whatever that means. I envisioned something maybe like this. You can go one curvy unit this way and two curvy units this way to get to the point 1, 2. In polar coordinates, you start with a pole and a ray called the polar axis, off of which you measure angles to other rays and distances along those rays. Coordinates are given as r and theta. In polar coordinates, the foliations are circles of constant radii and then rays with constant angles. An interesting aspect about polar coordinates is that the points in the plane are not uniquely described. You can have a point 1, 2, 3 units out and 0 radians. That will give you the same point as 3 units out and 2 pi radians, all the way around, describing the exact same point. You can even have -3 and pi radians. If the angle is pi, and the radius is -3, negative radii go in the opposite direction that you point your nose in to look into the direction of the angle. So if your nose is pointing in this direction, a negative radius will take you back 1, 2, 3 units to this same point. You can use polar coordinates to describe various regions in the plane. Suppose I have this region from theta equals 0 to theta equals pi over 2, and the radius at each of those angles goes from 0 to 3. I can describe that region R by 0 is less than or equal to R is less than or equal to 3, and 0 is less than or equal to theta is less than or equal to pi over 2. A sort of region that you should be aware of might be something like this. The region between two circles in the plane. This is called an annulus, after the annular rings of a tree, the root being annum, like year. Something is superannuated if it is really old and obsolete, kind of like me. An annulus, this annulus, can be described by 1 is less than or equal to r is less than or equal to 3, and 0 is less than or equal to theta is less than, you can put equal to if you wish, 2 pi. We need to know how to calculate areas and double integrals in polar coordinates. In particular, let's suppose that we have some region, and this region is bounded between some theta naught and theta final, and maybe r equals some function of theta. What we are going to do is we're going to take a thin slice of with d theta, but we are also going to slice it thinly dr. So if we have a radius r for the inner slice, the outer slice is at r plus an infinitesimal dr. And we want to calculate this little element of area. How big is the area inside of that little region? We're going to need to know the area formula for the sector of a circle of radius r and angle theta. You can get this by thinking proportionally. Theta divided by 2 pi, that's the proportion of the angle theta to all the way around, is equal to the area of the sector divided by the area of the entire disk of radius r, which is pi r squared. It follows then that the area of the sector is 1/2 r squared theta. The way to calculate the area element for this little tiny slice is to take the area of the sector with radius r plus dr all the way back to the origin, and then to subtract the area of the inner sector of radius r. So the element of area will be 1/2 r plus dr squared d theta minus 1/2 r squared d theta. D theta being the measure of this little infinitesimal angle. We can factor some of the things out here. The element of area is 1/2, and on the right hand side we're going to put d theta, which also factors out. R plus dr squared is going to be r squared plus 2r dr plus dr squared, and then we subtract r squared. Now, what can we factor out? We can factor out a dr. In the limit, as dr goes to 0, this term will vanish. And we get 2 and the 1/2 cancels. That gives us r dr d theta. The element of area in polar coordinates is r dr d theta. In the TV show The Simpsons, the daughter, Lisa, was studying integration in polar coordinates, and she kind of thought of this r dr d theta sounding a bit like a pirate. R dr dr r r. Don't forget this r. R dr r r. Let's validate this on some regions that you already know the area of. So for example, let's suppose we have a disk of radius r. The area is pi r squared. The area should also be the integral of the area element over this region. I'll use a fancy r to describe the region. This will be a double integral, and the element of area will be r dr d theta. Theta will go from 0 to 2 pi all the way around, and the radius will go from 0 to big R. Now, there are a couple things I'd like you to notice here. One thing is that on the inner integral, once you integrate and evaluate the endpoints, since all of the limits of integration are constant, this integral will give you a constant. And if you integrate that constant on an interval of length 2 pi, you'll just get 2 pi times that constant. We can write this as 2 pi times the integral from 0 to r of r dr right now. That's because if you integrate from a to b, any constant times dx, you get that constant times the length of the interval. That's true because you're just finding the area of a rectangle. Constant height times the width, which is b minus a. In this case, The width is 2 pi. The constant is whatever that integral is. I like to tell my students that you get 2 pi for free. You can also see this because of Fubini's theorem. You can reverse the order of integration because all of the limits of integration are constant. And if you integrate with respect to theta first, there are no thetas, so you end up with whatever you have, r, times the length of the interval, 2 pi. Either way, you get the 2 pi for free. Now, we have 2 pi, r squared over 2 evaluated from 0 to big R. The 2's cancel, and when we evaluate, we get pi r squared. Go figure. On our next problem, I want to integrate on a region R x squared plus y dA, where r is the annulus, inner radius 2, outer radius 4. Now, there are a couple things I want you to notice from this example. One is that an integral is a kind of limit of sums. They're sums. I'm adding up y's. I'm adding up y's on a region where there are just as many positive y's as negative y's. If I do that, shouldn't this term contribute nothing to the answer? Shouldn't the integral of y over a region that's symmetric through the x-axis give you nothing? Sure it will. Here's what we'll do. The region is symmetric in kind of a rotational way. It's easiest to describe the limits of integration in polar coordinates. So we're going to use polar coordinates for the integral. X in polar coordinates is r cosine theta. So the first term is r squared cosine squared theta. The second term is y, and y is r sine theta. dA. dA is r dr d theta. Theta will go from 0 to 2 pi, and r will go from 2 to 4. Notice that by Fubini's theorem we can reverse the order of integration and integrate with respect to theta first. If we do, when we integrate sine from 0 to 2 pi, you must get nothing. We can see right now this second term contributes nothing, but we should have seen that earlier from this level, knowing the symmetry of the region, that it's symmetric through the x-axis, and we have an odd function of y, then we must get 0. The other term is squared. You have to get something positive from that. Now, we'll integrate with respect to r first and ignore the second term. We have r cubed. Cosine squared is coming along for the ride. The integral of r cubed is r to the 4th over 4. What is 4 to the power 4? Well, 4 squared is 16. 16 squared is 256. To integrate cosine squared, we need the half angle identity, 1/2, 1 plus cosine 2 theta. And what's left over, we'll have 256 fourths. 2 to the power 4 is 16. Four goes into 256 64 times, and 4 goes into 16 4 times, so we end up with 60 divided by 3 is 30. Now, before integrating what's left, I want you to think about it. Cosine 2 theta, what is the period of that function? If I have cosine omega times theta, the period is 2 pi divided by omega. So in this case, the period is 2 pi divided by 2. That means that between 0 and 2 pi, we're going to complete 2 cycles of the cosine curve. If you integrate to pi over 2 in this case, you get half a positive bump, half a negative bump. Over 1 complete period, you get nothing. Over 2 complete periods, you get doubly nothing. So this term contributes nothing. What's left over is a constant 1 on an interval of length 2 pi. The integral will give you 1 times 2 pi times 30 is 60 pi. As you might recall, a sphere is the set of points a fixed unit away from the origin. They satisfy the equation x squared plus y squared plus z squared equals r squared. So if I write z equals the square root of 4 minus x squared minus y squared, putting the x squared and the y squared over and taking the positive square root, I don't get the whole sphere. This is going to be a sphere of radius 2, but it's only the top half, because I'm choosing non-negative values for the z. Let's suppose that I want to find the volume above the xy plane but below the sphere, but I don't want all of it. I only want the portion of radius 1, the core. To find the volume, we need to integrate this function over the region parameterized by r between 0 and 1, theta between 0 and 2 pi. So we'll set this up as a double integral. The integrand may be transformed as the square root of 4 minus r squared. The element of area in polar coordinates is r dr d theta. Don't forget the r. R will go from 0 to 1 and theta from 0 to 2 pi. There are no thetas on the interior here, not even on the limits of integration, and so we get 2 pi for free. We have then 2 pi times the integral from 0 to 1 of r square root 4 minus r squared dr. Name the method of integration. You have basically 4 methods of integration. You have use substitution, integration by parts, trigonometric substitutions, and partial fractions. You should probably think of them in the following order. If you have the derivative of something lying around, it's a u sub. If your integrand is a rational function, what is a rational function? Is a rational function a function that talks and makes sense? No. A rational function is a function that can be expressed as a ratio of 2 polynomials. A polynomial divided by a polynomial. This integrand is not a rational function. Trigonometric substitutions apply if you have a sum or difference of squares under a radical, which we do have, but we also have the derivative of something lying around. So this is a u sub. You usually use integration by parts as a last resort. In this case, u is the thing that has its derivative lying around, 4 minus r squared. So du is minus 2r dr. The minus we need to get rid of. The 2 we kind of have lying around as well. I'm going to put this into a box because this is a side computation. The integral is pi times the integral. I'm going to switch the limits of integration. I like to do this whenever I have a definite integral and I'm using the method of substitution. If r is equal to 0, then u is equal to 4. And if r is equal to 1, then u is equal to 3. We get a minus du u to the power of 1/2, and this is our transformed integral. Whenever I have the limits of integration such that the lower limit is bigger than the higher limit, I like to reverse those. The price you pay is a minus. We happily have a minus to give. So this is going to be pi times u to the power of 3/2 times 2/3, evaluated from 3 to 4. You can see that I switched the order of the limits of integration and paid for it by eliminating the minus out front. Now, we're going to calculate numbers to the power of 3/2. Anytime I have a to the power of 3/2, I want you to think of that as a to the 1 plus 1/2, which is a times the square root of a. We're going to have 2 pi over 3, 4 to the 3/2. That's 4 root 4, or 8, minus 3 to the 3/2. That's 3 root 3. Remember what the answer of this double integral represents. It's the core inside of the semi-sphere. It's the volume of this core. It's as though we took an apple and sliced it in half, and then we drilled a core out of it. The volume of that core is this value. In our next example, I want to find the area of one petal of the rose r equals the cosine of 3 theta. When you graph this rose, you'll find that it looks something like, well, it actually goes through the origin here. And to find the area of one petal, it's sufficient to integrate from 0 to the first place where it intersects the origin and double that. So we need to find the area, which we can calculate by a double integral up against an area element. In polar coordinates, the area element is r dr d theta. We need to figure out where the curve goes through the origin, so we need to solve 0 equals cosine of 3 theta. Cosine goes through 0 first at pi over 2. We deduce that 3 theta is pi over 2, which gives us theta equals pi over 6. So we'll integrate twice as theta goes from 0 to pi over 6. For each of those thetas, the radius will go from 0 out to the curve, from 0 to cosine of 3 theta. We are only integrating the area element because we're looking for the area of the region. So the integral will be of r dr d theta. We do not get a pi over 6 for free because we have theta in one of the limits of integration. We have to integrate this straight up. Integrating with respect to r first, we'll have r squared over 2, evaluated from 0 to cosine of 3 theta. The dr goes away with the inner integral. The d theta is still associated with the integral, with the theta limits. We have the integral from 0 to pi over 6 of cosine squared 3 theta d theta. Now, remember that cosine squared of x is 1/2 times the quantity 1 plus cosine of 2x. And also, sine squared x is 1/2 times 1 minus the cosine of 2x. So we will have 1/2 times the integral from 0 to pi over 6 of 1 plus the cosine of 6 theta d theta. What is the period of this function? The period is 2 pi divided by 6, or pi over 3. We're integrating from 0 to pi over 6, this cosine function. We're integrating over half the period. What happens if you integrate cosine over half a period? You got nothing. This part will contribute nothing. This is an efficient way of calculating integrals. This is something I want you to be expert at. You need to know how to do this. What's left over is the constant 1/2 times the length of the interval, pi over 6. The answer is pi over 12. Let's suppose that we have a surface described by z equals 4 minus x squared minus y squared, and we're looking for the region bounded between this surface and the surface described by z equals 0. First of all, do you recognize what kind of surface this is? We have here a kind of quadratic surface called an elliptic paraboloid, because both of the coefficients of the squared terms have the same sign. It's an elliptic paraboloid. If the signs were different, it would be a hyperbolic paraboloid. Because both are negative, this elliptic paraboloid will open down, intersecting at z equals 0 on a circle of radius 2, peaking at a height, when x and y are 0, of 4. We want to know the volume inside of this elliptic paraboloid above the plane z equals 0, the xy plane. So we need to integrate over the region, the domain, that is the base, the function 4 minus x squared minus y squared times an area element. That will give us the volume. For a couple of reasons, we should definitely use polar coordinates. First of all, the domain that we are integrating over is a disk of radius 2. That's easiest to set up in polar coordinates. The function also is amenable to translation to polar coordinates. We'll have the integral from 0 to 2 pi and from 0 to 2. That will cover the disk of radius 2 in the domain. The integrand is transformed as 4 minus r squared, and the area element is transformed as r dr d theta. Notice that there are no thetas in the integrand or in the inner limits of integration. We get 2 pi for free. When we distribute the r, the integrand is 4r minus r cubed. Integrating with respect to r, we get 4r squared over 2 minus r to the 4th over 4. And we're evaluating from 0 to 2. Notice that we've done two integrals at the same time. What do we get when we evaluate? Plugging in 2 squared is 4 times 2 is 8, minus 2 to the 4th is 16 divided by 4 is 4. 8 minus 4 is 4 times 2 is 8. 8 pi is the volume. 8 pi cubic units. In our next example, I want to integrate from minus infinity to infinity e to the minus x squared dx. This is not only complicated because the integral is improper. Do you remember what an improper integral is? Is an improper integral an integral that says inappropriate things in social settings? No. In this case, it's improper because one or more of the limits of integration is plus or minus infinity. The other thing that can make an integral improper is if you're integrating over a region that contains a discontinuity for the function. In this case, we have an additional complication. In particular, the integrand has no elementary antiderivative. So it is impossible to express the antiderivative of this integrand with a finite number of algebraic operations, or even trigonometric functions or exponential functions, we can't do it with a finite number of operations. That means we can't integrate this using the fundamental theorem of calculus because we can't find the antiderivative. What I'm going to do is I'm going to set the integral equal to a constant I, and I'm going to look at I squared, the integral times itself. It shouldn't matter what I call the variable, because after I evaluate the limits of integration, I end up with a constant. But I can combine these two integrals now. I can write this as the integral from minus infinity to infinity, the integral from minus infinity to infinity of, when I combine the integrands, I'll get e to the minus x squared minus y squared dx dy. And dx dy is the element of area in rectangular coordinates. I should probably switch, though, to polar coordinates, given the minus x squared minus y squared, which I can simplify to minus r squared. As you can see, I'm integrating over the entire xy plane. How do I integrate over the entire plane in polar coordinates? Theta will go from 0 to 2 pi. The radius will go from 0 to infinity. The integrand transforms as e to the minus r squared. So far, no real advantage. The real advantage comes when I translate the rectangular element of area to the polar element of area. R dr d theta. Now I have the derivative of something lying around. I can use u substitution to evaluate this integral, and what is more, for the outer integral, I get 2 pi for free. We're going to set u equal to minus r squared so that du is minus 2r dr. We have the r dr, but we don't have the minus 2, so I'm going to move that over to the other side. We have the 2 pi for free, but we get a minus 1/2 out front. If r is equal to 0, u is 0, and as r goes to infinity, u goes to minus infinity. E to the u, and there's the minus 1/2 du. We can flip the order of the limits of integration. We'll have pi, the integral of e to the u is e to the u. Flipping the order of the limits to get rid of the minus, we'll have the evaluation from minus infinity to 0. Now technically there should be a limit going on here. When you plug in 0, e to the 0 is 1. In the limit, as the u goes to minus infinity, e to the u will go to 0. We get a value of pi, but remember that's equal to the integral squared. It follows that the integral that we started with, from minus infinity to infinity of e to the minus x squared dx, the value is the square root of pi. I want to do one more example. Find the area of the inner loop of the limacon r equals root 3 minus 2 sine theta. See that little doohickey on the bottom of the C? That's called a cedilla, a diacritical mark called a cedilla. Limacon. How does this limacon look? When theta is 0, the radius is root 3. As theta goes to pi over 2, you end up with root 3 minus 2, which is negative. By the time you get to pi, sine of pi is 0, you're back out to a radius of root 3. And at 3 pi over 2, sine is minus 1, you get a maximum radius of root 3 plus 2, and then back to root 3. I want to know the area of the inner loop. So we need to know where the curve crashes through the origin. We'll set 0 equal to root 3 minus 2 sine theta and get sine theta is root 3 over 2, a positive value. We expect there to be two positive values, one in the first quadrant, one in the second quadrant, and sine is positive in quadrants 1 and 2. The reference angle is pi over 3, so 2 pi over 3 will be the angle in the second quadrant. Though it may be best to integrate to pi over 2, from pi over 3 to pi over 2, and just double the result. The area is the integral over the region of the area element. We will double the integral from pi over 3 to pi over 2. On all of these, the radius will go from 0 to the curve. The area element is r dr d theta. We don't get any angles for free here because we have a theta in the limit of integration. So we'll get the integral from pi over 3 to pi over 2. The integral of 2r is r squared. The dr went away with the integral with respect to r. Evaluating, we get the integral from pi over 3 to pi over 2. We'll have root 3 minus 2 sine theta quantity squared d theta. Foiling out this perfect square, we have the integral from pi over 3 to pi over 2 of 3 minus first times last times 2. That's 4 root 3 sine theta plus 4 sine squared theta d theta. Remember that when you're integrating sine squared x is 1/2 1 minus cosine 2x. So we're going to have 4 times 1/2 1 minus cosine 2 theta. When we distribute this 2, we'll have 2 plus 3. That's 5. Minus 4 root 3 sine theta minus 2 cosine 2 theta d theta. Integrating, we have 5 theta. The integral of sine is negative cosine. We'll get plus 4 root 3 cosine theta minus, when you integrate cosine 2 theta, you get 1/2 sine 2 theta, which cancels this 2. We'll end up with the sine of 2 theta, evaluated from pi over 3 to pi over 2. Minus 1 point for each of the trig function evaluations that you get wrong. I'll show you a way to remember those, but first, let's finish this problem. We're going to have 5 times pi over 2 plus the cosine of pi over 2 is 0. 2 times pi over 2 is pi. The sine of pi is also 0. We'll subtract what we get when we plug in pi over 3. That's 5 pi over 3. The cosine of pi over 3 is 1/2. The sine of 2 pi over 3, 2 pi over 3 is in quadrant 2. Sine is positive in quadrant 2, the reference angle being pi over 3. We get minus root 3 over 2. 1/2 minus 1/3 is 1/6. So we have 5 pi over 6 Perhaps we shouldn't have canceled the 2 here, written this 4 over 2 times root 3. 4 of them minus 1 of them is 3 of them, and we're subtracting, we get minus 3 root 3 over 2. I promised you I would show you a way to calculate the values of the trig functions simply. Let's write out the sine of 0, the sine of pi over 6, the sine of pi over 4, the sine of pi over 3, and the sine of pi over 2. An easy way to generate this table is to count from 0 to 4. And then it's root over 2, root over 2, root over 2, root over 2, root over 2. And all of those values are correct. Cosine just goes the other way. For tangent, the values go in increasing order, just like the graph, always increasing between negative pi over 2 and pi over 2. Zero, 1 over root 3, 1 root 3, and then undefined. These go in increasing order. I'd like to move on to triple integrals. These are defined over some 3D region in space, and we want to slice these up. We want to find a partition of those. We're going to cut out little volumes, and in those little volumes we'll have sampling points C sub k, and we're going to define the integral over R of some function up against a volume element to be the limit. The norm of the nth partition is going to be the maximum diagonal across these little cubic pieces from one end here to the other corner, catty corner. That will be the maximum size of one of those little diagonals will be the norm of the partition. We'll add up as k goes from 1 to n, f of ck times these little delta vk's, where delta vk will be the volume of that little region. These are also sometimes written as the triple integral of f up against a volume element. I like to save my effort by just writing the single integral. I'll know that it ends up being a triple integral because I'm using a volume element. Now, no one really wants to calculate integrals, double, triple, any kind of integral, using limits of Riemann sums like this. We need a theorem similar to what we found with double integrals. For double integrals, the silver bullet was Fubini's theorem. We demand a Fubini's theorem. To properly phrase Fubini's theorem, let's suppose we have some region in space it has a lower surface and an upper surface. The lower surface is going to be described by z equals g1 of xy, and the upper surface is described by z equals g2 of xy. And this is going to be our region. This whole region is going to project down into the xy plane, into a region in the plane like this, which has a lower limit on the x of a and an upper limit on the x of y. It's bounded below, looking from this direction, using vertical cross sections this way, by a curve y equals h1 of x and y equals h2 of x on the top. In this case, the region R is described as follows. A is less than or equal to x is less than or equal to b. Y is between h1 of x and h2 of x. And z is between g1 of xy and g2 of xy. Fubini's theorem says that the integral on R of f dv is the integral from a to b, the integral from h1 of x to h2 of x, lower curve to upper curve, and then the integral from lower surface to upper surface, f of x, y, z, dz, dy, dx. You can see these are the z limits of integration, and then the y limits of integration, and then the x limits of integration. Fubini's theorem allows us to replace a limit of crazy Riemann sums in terms of iterated integrals instead. Properties of the triple integral are, as you might expect, the integral on some region of a constant times f is a constant times the integral on R of f dv. You can see that constants pull out of sums and out of limits. So this theorem is true. If you have f plus g, you can integrate f first and integrate g next. Calculate those integrals independently. Same is true for minus. If f of x is bigger than or equal to 0 for all x in the region R, then when you integrate on R f dv, you can't get a negative value. Property 4, if f dominates g within the region R, then the integral of f will be bigger. Also, if you can divide some generic kidney-shaped region into two pieces, if the whole thing is R, the top is R1 and the bottom is R2. If R can be decomposed as the union of two regions that have no overlap, then integrating on R is the same as integrating on R1 plus the integral on R2. How do you find the average? Well, it's 1 over the volume of the region times the integral over the region of f. This is similar to what you did way back in Cal1. In Cal1, the average of some function on an interval ab was 1 over b minus a, the integral from a to b of f of x dx. B minus a is just the length, and in one dimension, that is the size of the set. In 3 dimensions, the size of the set is its volume. Suppose I want to calculate the integral from 0 to the square root of pi over 2, the integral from x to the square root of pi over 2, and the integral from 1 to 3, the sine of y squared, dz, dy, dx. The integrand does not depend upon z, so when integrating with respect to z, we treat sine of y squared as a constant. That constant times its interval length gives us the integral from 0 to root pi over 2, the integral from x, root pi over 2, and then twice the sine of y squared dy dx. Twice because 3 minus 1 is 2, 2 times the height, which is the function value, that being constant with respect to z. Now, sine of y squared has no elementary antiderivative, which means it's impossible to proceed unless we think of something. Let's think about the region that we are integrating over. X goes from 0 to root pi over 2. We go from y equals 0. We go from y equals x to y equals root pi over 2. The region that we're integrating over is this triangle, with our differentials being dy followed by dx. We are currently using vertical cross sections. It might be good to switch to horizontal cross sections. Let's see what happens if we do that. When we do, we're going to have to write this as dx dy, where y will be the limits that are constant now. Y will go from 0 to root pi over 2. X will go from lower curve to upper curve, the lower curve being x equals 0, the upper curve being x equals y. Now, when integrating with respect to x first, the 2 sine y squared is constant. And so we take that constant and multiply by the length of the interval. We get the integral from 0 to the square root of pi over 2 of 2y sine of y squared dy. Now we have the derivative of something lying around. We can evaluate this integral using the method of substitution. We'll set u equal to y squared so that du is 2y dy. If y is equal to 0, then u is 0. If y is the square root of pi over 2, u is pi over 2. The 2y dy goes away to become du, and sine of y squared becomes sine of u. We're integrating sine from 0 to pi over 2, but you know this one. We're getting half a bump. Half a bump gives you 1. The answer is 1. I want you to think carefully about every step in this last example. The ability to reverse the order of the limits of integration is an important skill, and we had to think carefully about how to do that and still integrate over exactly the same region. Vertical cross sections versus horizontal cross sections. Also, you need to know the standard tricks of the trade. I would like to calculate the following triple integral. The integral from 0 to 2, the integral from 0 to x, the integral from 0 to x plus y. The integrand is e to the y times the quantity, y plus 2z, and then times dz dy dx. We integrate with respect to z first. Everything not involving z will be constant. We'll have the integral from 0 to 2, the integral from 0 to x. E to the y is coming along for the ride. We'll have yz plus z squared evaluated from 0 to x plus y, dy dx. Evaluating, we'll have y times the quantity, x plus y, plus the quantity, x plus y squared, dy dx, and then minus 0. Let's simplify this before integrating. Multiplying this out, you can see that we'll have an x squared, a 2xy plus another xy gives us plus 3xy, and then we'll have a y squared and another y squared, so plus 2y squared. all of that is multiplied by this e to the y. We're integrating with respect to y, so x is constant in this integral. What is the method of integration? You might have guessed this is an integration by parts problem, but it's kind of a complicated one because there are three terms. We can do them all together, and we should definitely use the tabular method since we have a y squared. Otherwise, we'll end up doing integration by parts at least twice, if not 3 times. Here's the way to do it. You'll have u and dv. dv is the thing you want to integrate, that's e to the y. U is the thing you want to differentiate. That's x squared plus 3xy plus 2y squared. You differentiate down the first column and integrate down the second column. In both the derivatives and the integrals, it's with respect to y. The derivative with respect to y is going to be 3x plus 4y, and then 4, and then 0. That's where you stop. You integrate down the second column with respect to y. That's e to the y, e to the y, and e to the y. Multiply down diagonals and alternate signs, plus, minus, plus. We get the integral from 0 to 2. It's going to be x squared plus 3xy plus 2y squared e to the y minus 3x plus 4y e to the y, and then plus 4 e to the y. Evaluated from 0 to x, all times dx. Plugging in x for y, we'll have x squared plus 3x squared plus 2x squared is 6x squared e to the x. And then we get minus 7x e to the x, and then plus 4 e to the x. But then we need to subtract what we get when we plug in 0 for y. Let me write that down here. Plugging in 0 for y, e to the 0 is 1 times x squared. E to the 0 is 1. Y is 0, so we get minus 3x. And plugging in 0, it's plus 4. All times dx. We can factor the e to the x out on the first grouping. Name the method. Looks like the best choice is the tabular method for integration by parts on that first term. On the second term, it's just the power rule for antiderivatives. For the tabular method, dv is, of course, e to the x. U will be 6x squared minus 7x plus 4. We differentiate down the first column. That's 12x minus 7, 12, and 0. That's where you stop. Integrating down the second column, it's just all e to the x. Multiply down diagonals and alternate signs, plus, minus, plus. We're getting 6x squared minus 7x plus 4 e to the x minus 12x minus 7 e to the x plus 12 e to the x, and then minus x cubed over 3 plus 3x squared over 2 minus 4x, all evaluated from 0 to 2. Plugging in 2, we'll have 2 squared is 4 times 6 is 24. 24 and 4 is 28, but we're subtracting 14. So that gives you 14e squared. Minus 24 minus 7 is 17, minus 17e squared, plus 12e squared, minus 8 thirds, 2 squared is 4, divided by 2 is 2, times 3 is 6, minus 8. And then we subtract what we get when we plug in 0. Plugging in 0, we'll have 4 minus a negative 7 minus 12. And then the polynomial part will contribute 0. So what do we get? 14e squared minus 17e squared is negative 3, plus 12 is 9e squared. 6 minus 8 is minus 2. 4 and 7 makes 11, plus 12 makes 23. And then we should convert everything to thirds. We have minus 8 thirds, minus 6 thirds, and minus, well, 23 times 3 is 69 thirds. We have then 9e squared minus 8 minus 6 is minus 14, minus 69 is minus 83 thirds. I would like to set up, but do not evaluate, triple integrals to find the volume of the following regions. First, I need the first octant part of the solid bounded by the cylinder z equals 1 minus y squared, and the planes x plus y equals 1, x plus y equals 3. So the first octant part. Let's look at this cylinder first. Let's draw the first octant. That's all we will need. Z equals 1 minus y squared. And the yz plane would be a parabola, opening down, peaking at a height of 1. But since x is unconstrained, this represents a cylinder. We can slide this along the x-axis, generating a sheet like this, a cylinder. We have the plane, x plus y equals 1. Now, in the xy plane, that would be a line. But we slide that along the z-axis, and that gives us a curve, a sheet, a plane. We also have the plane x plus y equals 3. That's going to slice in this direction. We're going to get another piece coming off like this. So the solid that we are interested in is the solid above this little rhomboid-shaped region here, this little diamond, above that, and below this little slanting sheet. How do we set up the integral to find that volume? We can project everything into the xy plane, and the region that we'll integrate over in the xy plane will go like this. So, how do we do this? What cross-sections do we want to use? If you use vertical cross-sections, you'll have to break this up into 3 triple integrals. It's probably better to use horizontal cross-sections in this case. According to Fubini's theorem, the volume will be a triple integral. The volume element that we're integrating is dz dx dy, since we're going to be using horizontal cross-sections in the xy plane. We integrate z from lower surface to upper surface. The lower surface is the xy plane, z equals 0. The upper surface is given by z equals 1 minus y squared, that parabolic cylinder. Then the y-coordinates will go from 0 to 1, and the x-coordinates will go from lower curve to upper curve. Remember, the lower curve was x plus y equals 1. That's x equals 1 minus y. That's the lower curve. This upper curve was x plus y equals 3, or x equals 3 minus y. And that gives us the upper limit of integration. This will give us the volume of that solid. On part B, I want to find the volume of the solid bounded by the upper hemisphere, z equals the square root of 1 minus x squared minus y squared, and z equals 0. Since the radical symbol represents the principal square root, which is always the non-negative one, we end up with only the upper hemisphere. Find an integral representing the volume. Fubini's theorem would have us project this down into a domain of parameters in the xy plane. The x limits of integration will be determined by that projection down into the xy plane. The z limits will be from lower surface to upper surface. If you think about the projection down into the xy plane, that's going to be a disk of radius 1. What coordinates would you prefer to integrate over a disk? It seems to me that you would want to use polar coordinates. So we will use a dz, but instead of dx and dy, it's going to be r dr d theta. Theta will go from 0 to 2 pi, and the radius along any spoke will go from 0 to 1. The z will go from the lower surface, z equals 0, to the upper surface, which we will convert to polar coordinates. Z equals the square root of 1 minus r squared. That will give us the volume. On part C, I want to find the region between z equals the square root of 6 minus x squared minus y squared and z equals x squared plus y squared. The top is a sphere and the bottom is an elliptic paraboloid opening up. So I'll have this elliptic paraboloid being capped by a piece of sphere. It's as though I have shaved ice packed into a container shaped like an elliptic paraboloid, kind of sloping off on the top in a semi-spherical piece. It's as though I have a cup shaped like an elliptic paraboloid packed full of shaved ice, kind of sloping off across the top like this. Let's set up a triple integral to find the volume, but to do that, we need to know where the sphere intersects the elliptic paraboloid. So how are we going to find the intersection of these two? There's a tricky way to do this. Instead of setting the z's equal to each other and solving for x and y, which we could do, one thing you might do is instead replace x squared plus y squared with z. Let's try that again. Instead of setting z's equal to each other and figuring out x squared and y squared from that, it might be easier to just replace x squared plus y squared with z. That gives z equals the square root of 6 minus z. Squaring both sides, z squared is 6 minus z. That gives you z squared plus z minus 6 equals 0. All we have to do is solve for the roots of this quadratic equation. And you know how to solve every quadratic equation. But this one looks easy to factor. Z plus 3, z minus 2. They have to have opposite signs, and the bigger one has to be positive. So it looks like we get z equals minus 3 or 2. We can throw out the minus 3 because z can't be negative. Z equals 2. These will intersect at z equals 2. But where is that on the xy plane? How does that project down onto this disk down in the xy plane? If z is equal to 2, we have x squared plus y squared equals 2, and that gives us a circle, a disk, of radius square root of 2. Since the projection down into the xy plane is a disk, we'll use polar coordinates on the instead of x and y. the xy plane, theta will go from 0 to 2 pi. The radius will go from 0 to the square root of 2. On the z limits of integration, we go from lower surface to upper surface, looking from below. The lower surface was z equals x squared plus y squared, which, converting x and y to polar, gives us z equals r squared. The upper surface was z equals the square root of 6 minus x squared minus y squared. We'll write that as the square root of 6 minus r squared. I would like to talk about two different coordinate systems that we're going to use in R3, in space. Cylindrical and spherical. Coordinates. Cylindrical coordinates are actually pretty easy. In the xy plane, you can use theta and r to describe points and then just tack on a z to lift yourself out of the xy plane. These are going to be cylindrical coordinates. They obviously relate to rectangular coordinates in the following ways. You have x equals r cosine theta, y equals r sine theta, and z equals z. In this way, if you know r, theta, and z, you can figure out x, y, and z. On the other hand, r squared is x squared plus y squared by the Pythagorean identity. Tangent theta is y over x by the ratio identity, and z equals z. In this way, if you know x, y, and z, you can figure out r, theta, and z. The theorem of Pappus gives us a very simple way of calculating volume elements in cylindrical coordinates. You have a little slice of width d theta here, and we're going a little slice dr at some r. So if you raise this up, and you have a little slice dz, what is the little volume element, dv? Well, the little area element in the xy plane is r dr d theta. Go figure. By the theorem of Pappus, you can get the volume element by taking that area element and multiplying by how far you sweep it. That's going to be dz. So it's dz r dr d theta. This is something you need to memorize. Let me write that down again. The volume element for cylindrical coordinates, dv is dz r dr d theta. Cylindrical coordinates are almost always great to use if the region that you're working with has rotational symmetry around the z-axis. So, for example, let's find the volume of the region bounded by z equals 4 minus x squared minus y squared and z equals 0. Here we have an elliptic paraboloid intersecting the xy plane in a circle of radius 2, peaking at a height of 4. Find an integral for the volume. This has rotational symmetry around the z-axis. It's probably best to use cylindrical coordinates. So we'll write z equals 4 minus r squared versus z equal to 0. The volume element is dz r dr d theta. The region does, the lower surface is z equals 0, and the upper surface is z equals 4 minus r squared. theta will go from 0 to 2 pi, and the radius will go from 0 to 2. Let's calculate this integral. Integrating with respect to z first, the integrand only has this little r. It doesn't have anything involving z. And one other thing that you can point out is there are no thetas in here. Since there are no thetas, the outcome of the first two integrals will be a constant. If I integrate that constant from 0 to 2 pi, I get 2 pi times whatever that constant is. That means I will get 2 pi for free. The r integral will go from 0 to 2. The z integral is of a constant relative to z. You just get the integrand times the length of the interval. Here we've done two of the integrals simultaneously. The integral on theta just gives you 2 pi times everything else, and then the integral with respect to z, constant times the length of the interval. Distributing, we now have 4r minus r cubed. So using the power rule, we get 2 pi times 2r squared minus r to the fourth over 4, evaluated from 0 to 2. Plugging in 2 squared is 4 times 2 is 8. 2 to the fourth is 16 divided by 4 is 4, and then subtracting 0, 8 minus 4 is 4, times 2 is 8. The answer is 8 pi cubic units. Notice that in cylindrical coordinates, if you use r equals a constant, theta not constant, z not constant, you can take that circle at a constant radius in the xy plane and sweep it vertically, and that gives you cylinders. That's allowing for theta to be variable, z to be variable, but r being fixed at a constant. In spherical coordinates, you don't get cylinders. In spherical coordinates, one of the foliations involves nested spheres. That's because in spherical coordinates, to describe a point in space, one of the coordinates is the distance from the origin out to the point. That distance we are going to call by the lowercase Greek letter rho. The lowercase is this, the uppercase is this, it's pronounced R-H-O, rho. That's going to be one of our coordinates. Another coordinate will be this angle theta, and it might seem obvious to you to use this latitudinal angle, but we don't, alas. What we use instead is the angle off of the positive z-axis. That's called the colatitude. It has the symbol phi. The lowercase phi is like this, an uppercase phi is like this. This is phi, phi. That's the colatitude. It's like the angle off of due north instead of the angle up from the equator. You're accustomed to using this latitudinal angle. We're going to use colatitude. We'll list the coordinates in the order rho, phi, theta. What is the relationship between these spherical coordinates and rectangular coordinates? Let's make the associations here. We'll have x, y, and z. As you can see, if I label this distance as lowercase r, which is not either a rectangular or a spherical coordinate, it's a cylindrical coordinate, but we'll put it in there anyway, just for our work. Then you can see the following. X divided by r is adjacent over hypotenuse of a right triangle. That's cosine theta, and y divided by r is sine theta. We can move the r's over. But we need to get rid of these r's. We'll do that using the following relation. Note that if this is a line that goes straight up, this is also a line that goes straight up, which means these two lines are parallel, and they are cut by a transversal, which means this angle had better be phi. We have a right triangle here since this goes straight up off of the xy plane. That means compared to this angle phi, r is going to be the side opposite, whereas rho is the hypotenuse. So we get the sine of phi is r divided by rho. That means we can replace r with rho sine phi. Also note that z divided by rho is cosine phi. Putting this, and these two things together, we have the following. We had x equals r cosine theta, y equals r. Then x is going to be rho cosine theta sine phi. If y is r sine theta and r is rho sine phi, then y is rho sine theta sine phi, and z is rho cosine phi. I would like for you to memorize these conversion formulas. It also follows from the Pythagorean theorem that x squared plus y squared plus z squared equals rho squared. In addition, we have the following. Y divided by x will cancel the rho and the sine phi, leaving you with tangent theta. Now, how do you then find phi? To find phi, we have cosine phi is z divided by rho, and rho can be found from here. So with these formulas, if you know x, y, and z, you can figure out rho, phi, and theta. The important thing that we need to find is the volume element in spherical coordinates. We're going to do this in a couple steps. First, suppose I have kind of a d phi. And let's suppose that to begin with, that phi is set equal to pi over 2. So we're at a kind of a maximum size on these little volume elements. This is going to be our little volume element. To begin with, we'll set phi equal to pi over 2, so our little volume element, instead of being squished up here, will be way down here at its maximum size. If you go further, the little orange slice here will collapse back down to 0 size when we get back down to here. So how big is the volume element if we assume that phi equals pi over 2 and we make a little tiny jiggle here in the size of phi? Well, what you do is you take the area of this little piece. The area of that little piece in the xy plane, you'll recall, will be the element of area, which will be rho d theta. As long as phi is pi over 2, that little area will be rho d theta. Because when phi is pi over 2, rho will act just like r in cylindrical coordinates. But how far is this being swept if the little angle here is d phi? Well, you'll remember the following formula. If you have r and theta, the little arc length s is r theta, provided, of course, theta is measured in radians. In this case, we're sweeping this a certain distance, s. The little ds is going to be the radius, rho, times the little element of angle, d phi. So in this particular instance, the element of volume will be the element of area times how far you sweep it. That's going to be rho squared, d rho d phi d rho d phi d theta. But that's only true when your little element of volume is down there in the xy plane. That's kind of where you get the maximum element of volume. If phi is equal to 0, this will be squished down to 0 in volume. Same thing if phi is equal to pi. So it reaches its maximum at pi over 2, just like the sine curve reaches its maximum at pi over 2. We deduce then that the element of volume is going to be rho squared sine phi d rho d phi d theta. That's the one you need to memorize. The volume element in spherical coordinates dV is rho squared sine phi d rho d phi d theta. And of course you are going to memorize that right now. Let's calculate the volume of something that you already know the volume formula for. A sphere of radius r. The volume is 4/3 pi r cubed. We should be able to figure this out. We just integrate the volume element. Rho squared sine phi d rho d phi d theta. Theta will go from 0 to 2 pi. We're going to go all the way around. But phi goes from straight up to straight down. If the theta is going from 0 to 2 pi, going from straight up to straight down will cover all different vertical cross sections all the way around. So we need only go from 0 to pi on the angle phi. For rho, we'll go from 0 to the radius, r, and hope that this integral gives us 4/3 pi r cubed. First note that there are no thetas in the limits of integration or in the integrand on those first two integrals. We get 2 pi for free. By Fubini's theorem, we can integrate with respect to phi first. Integrating sine from 0 to pi gives us one bump. One bump gives you 2. Then integrating rho squared gives us rho cubed over 3. And so we get 4/3 pi r cubed. In our next example, I want to find the volume of the region bounded by the upper nap of the cone z squared equals x squared plus y squared, and z equals the square root of 1 minus x squared minus y squared. This surface, z equals the square root of 1 minus x squared minus y squared, is a hemisphere. It's only the upper part because of the principal square root, but it will have radius 1. We're only looking at the upper nap of the cone, so we have a cone that is being capped by a hemisphere. This is one of those cheap snow cones where they pack all the ice down and it's just barely mounded up. It's not some nice big sphere sitting on top. Oh, the cheap snow cone. Don't you just hate those? Let's find the volume. To set up the integral, we kind of need to know where these surfaces intersect. So we'll have to set them equal to each other somehow. Here's an idea. x squared plus y squared gets replaced by z squared. We'll plug that into here. If you square both sides now, you'll get 2z squared equals 1, or z equals 1 over the square root of 2, plus or minus, but it has to be plus. So if I drop an altitude here, the z is going to be 1 over the square root of 2, where this radius is the radius of the sphere, which is 1. This angle, then, will be adjacent over hypotenuse equals cosine. That angle will be the same as the colatitudinal angle where the cone meets the sphere. Cosine phi will be adjacent over hypotenuse, which gives you phi equals pi over 4. The variable phi, to sweep across this whole region, will go from 0 to pi over 4. Theta will go from 0 to 2 pi, and rho will go from 0 to 1 throughout the region. The volume of the cheap snow cone will then be the integral. We need to integrate the volume element, which is rho squared sine phi d rho d phi d theta, always in spherical coordinates. Rho will go from 0 to 1, phi from 0 to pi over 4, and theta from 0 to 2 pi. That will cover the entire region. As you can see, there are no thetas in here, so we get a 2 pi for free. Unfortunately, we're integrating sine phi from 0 to pi over 4, so we don't get any cheap trick on that one. Integrating rho squared, we'll have rho cubed over 3. We still have the sine phi d phi. Evaluating, we'll have 1/3, which will join the 2 pi out front to get 2 pi over 3. Then when we integrate sine, we'll have minus cosine phi evaluated from 0 to pi over 4. This gives us negative 2 pi over 3. The cosine of pi over 4 is root 2 over 2, and the cosine of 0 is 1. We'll distribute the negative 2. When we distribute the negative 2, we'll get a positive 2 and then minus the square root of 2, all times the pi over 3. What does this represent? That's that volume of the cheap snow cone.